Anybody around here? Okay, let's start with a recap. So last time we spoke about special relativity. We started to discuss special relativity. We said that the experimental basis, of course, is the Michelson-Morley experiment. And we said that based on that, if we have two observers, one in the O frame, O prime frame, another one is O prime. Both of them are in inertial reference frames, but not the same frame. And the time t equal to 0, x, y, z equal to 0, crest of light is being emitted. Then each one will argue that crest of light is at location x squared plus y squared plus z squared is equal to c squared t squared in the blue frame, and x prime squared plus y prime squared plus z prime squared is equal to c squared t prime frame. T prime squared in the prime frame. C is the speed of light. And since in general x is different than x prime, so then t will be different than t prime. So we'll disagree on the location of the event. We will disagree on the time. But there is one thing which both agree on, that is called the interval. So interval between two events is delta s squared is a minus, defined as a minus c delta t squared plus delta x squared plus delta y squared plus delta z squared. This is something that both observers agree on, and we said this is analog to the concept of distance in Euclidean geometry. Then we move on to define like a few definitions. So we define a 4-vector x with an upper index mu as x0 is ct, x1 is x, x2 is y, x3 is z. That's 4 components. It's a 4-vector in space-time known as Minkowski space. 4-vector of position in Minkowski space. Then we said that when we make use of only the spatial part, we'll use Latin indices. xi, we'll get that when we speak about cosmology. And then we define a matrix, eta mu, with 2 lower indices, which was defined as a -1, +1, +1, +1 on the diagonal, and then everything else was 0. And I told you that the same matrix, it has a name, it's called a metric. The same matrix appears in quantum field theory for the same reason, because also there we need to ensure that nothing travels faster than light, but with an opposite sign. eta q of t is minus eta gr. We'll stick here to the gr notation. And using these two matrices, we can write down the interval. Delta S squared in a very compact form. Sum of mu and nu equals 0 to 3 of eta mu delta x mu delta x mu. And to make our life simpler, when we're seeing the same index that appears twice on the same side of an equation, once as a lower index, once as an upper index, we understand that there is a summation, so we don't need to write it down. So we said delta S squared is just eta mu delta x mu delta x mu. And I stress again, if you get confused, which could happen at the beginning, simply add up a summation when you're seeing the two indexes on the same side. Once is up, once is down. Then we define the Lorentz transformation as any transformation that concerns the interval. We denote this transformation with a matrix, one upper index, one lower index. So x mu prime is lambda mu prime nu. They are not one on top of each other. Space here. You see today y. X nu. The requirement that concerns the interval was that it must fulfill that eta rho sigma is equal to lambda mu prime rho lambda mu prime sigma eta mu prime nu prime. What is the condition?
Lambda has both upper case and lower case index.
One upper index, one lower index.
Mm-hmm. Okay.
And the upper index is first, the lower index is second. And we gave a few examples. One example was a simple notation. Example, lambda mu prime mu equal 1 0 0 0 0 0 0 cosine theta sine theta 0 minus sine theta cosine theta 0 0 0 1. That is of course rotation in the xy plane. x0, x1, x2, x3. Which is a legitimate Lorentz transformation. And another one was lambda prime nu, was a rotation in the tx plane, which we call boost, cosine hyperbolicus of phi, minus sine hyperbolicus of phi, minus sine hyperbolicus of phi, cosine hyperbolicus of phi, 0 0 0 0 1 0 0 1 0 0 0 0. And we show, not fully, because we did not solve the full set of conditions here. So how many equations are there here? Total? How many equations are written here?
See, 256.
How many equations?
16.
16 equations, because we have equations for each row and sigma. Right? 4 times 4. And how many components are there in each equation? 16. So there are total 256 components. Luckily, most of them are zero, because this matrix is mostly zeros. Luckily for us. Of course, if you do it in a computer, the computer can give it what to do, still do it for you. But Einstein had no computers. And we show that this very abstract notation actually gives you what you're familiar with from first year special relativity course, what you're familiar from a Lorentz transformation, by identifying here beta as tangent hyperbolicus of phi, and gamma beta is sine hyperbolicus of phi, and gamma is cosine hyperbolicus of phi. That gives you what you're familiar from: Ct prime is equal to gamma Ct minus beta x, and x prime is gamma x minus Ct. These are things you're familiar with. Last thing we did was to discuss time dilation. So I'm carrying a clock with me, but you're seeing me and my clock moving. So from my perspective, my clock is not moving at all. Relative to me, my clock is static. Relative to you, it is moving. So relative to me, the clock ticks at proper time intervals. Okay. So delta t is dt is d tau. Relative to you, delta tau prime is 1 minus beta squared 1/2 delta t prime. Since d tau prime is equal to d tau, then we get that delta t prime is 1 minus beta squared minus 1/2 delta t, which is gamma delta t. So if you're seeing my clock moving, doesn't matter which direction, you'll always see it getting slower relative to the time that the manufacturer stated. So basically, if I'm moving, I'm staying younger relative to you. Think of that. Questions about anything we said last time? No? If there is a word in English you don't get, just ask me to translate it. But again, English is not your fault. Okay, move on. Okay. Now it's about the time that we speak a little bit more in depth into vectors. I introduced here 4 vectors, I just erased it. But now is the time to speak a little bit more. We'll do it in several times because we will develop the theory gradually. Not full now, because we don't need everything now, but just gradually, once at a time. So we're going to go back to linear algebra. So what we're going to do now is vectors and tensors. Call it 1, because there will be more. Come later. Okay, so we start by 4 vectors. Maybe I should start by asking you guys, what is a vector?
It's aligned with some direction, pointed to some direction.
Okay. Something which has a direction. Radius. I've been hanging with vectors since kindergarten. Why are you afraid to answer?
Couple of numbers in there.
It's not just numbers, right? It means something, these numbers. Oh, so it's direction. So line is direction, how do you describe it? Line is direction.
Yeah.
Well, we all agree this is a vector.
Yeah.
Well, the vector is more than 3 components, so it's not.
More than 3 components, yeah. I mean, obviously, in Minkowski space, how many components the vector is going to have? 4, of course. What is a vector? Come on. This is your 3rd year in university. Okay.
Maybe vector is a way how we can represent some physical quantities that have not only magnitude but also direction.
Essentially, yes. Vectors are up there because we need them.
Yeah.
Because they are good in representing physical quantities in a way. But why do we use vectors? We could use some other terms. There is something deep here, right? You realize that. No more clues? What is a vector? No idea. Okay. So I'm going to define a vector for you. I'm actually disappointed. What's a vector? No answer. You don't know what is a vector. You've been using it all along. Right. You had a whole course in linear algebra. Otherwise you wouldn't be. At least 1 course in linear algebra. Right?
Can we say that it's an array of numbers?
Array of numbers is one way of describing it, yes. But the numbers have some connection between them, right? I'm not just throwing numbers, right? 3, pi, and numbers, right?
Dimensions, maybe.
Yeah. How do you call these numbers? Components, right? Something has components.
Yes.
And what can we say about the vector? That there is what?
Then we change the coordinate system. These components goes
Right.
not
There is-
a random way.
Right. There is some relation between
Yeah.
the components of the vector,
Mhm.
not just random numbers. Right?
Mhm.
What happens to the vector, by the way? Okay, 1 step at a time. So I'm going to define a full vector. How am I going to define a full vector? Well, I've already presented one vector. X mu is a vector. X mu. It's a 4 vector of location. And what happens to the components of x mu when we change the coordinate system? They change. How do they change?
According to
Lorentz.
Lorentz transformation, right? The Lorentz transform, right? So when we change the coordinate system, x mu goes to x mu prime, which is lambda mu prime mu x mu, right? That is what happened to the components of the vector when we are changing the coordinates from O to O prime, right? Okay. And that's what I'm going to do to define a vector. So my definition of a vector, and to be more precise, it's actually called contravariant for vector, for reasons which will become clear shortly. So definition. A contravariant for vector is any quantity whose components undergo the transformation V alpha goes to V alpha prime, which is equal to lambda alpha prime beta V beta, when the coordinate system is transformed by x alpha goes to x alpha prime, which is lambda alpha prime beta, x beta. I'm making a transformation of the coordinate system, and any quantity whose components transform exactly the same way, I call it a 4-vector. The exact technical name is contravariant 4-vector, but when it goes to contravariant 4-vectors, I simply call them 4 vectors. I will not say contravariant mostly. Obviously, it has 4 components. Dimension of 4. Okay. So 1, it has 4 components, so 4 dimensions. Two, there comes a very subtle part. Vectors are attached to a single point in space-time. It's very important. Or attach it right now. Are located at a given point in space-time. Okay, so you said that you're used to think of vectors as arrows. That's true. We'll keep on using that. We'll still present vectors as arrows. But the arrows are not connecting 2 points, as you might have thought. The vectors belong to a single point. Where this is becoming crucial? when the space is not flat. So let's think of that space. There's a point P on that space. Okay. Think of the surface of the Earth. The technical name for such a space is called a manifold. Yeah. Okay. And what we really do is we take this space. Okay, I'll give you a hand-waving definition of what is a manifold. Okay, we'll talk about it more later. Right now, a manifold is a space that locally looks Euclidean, but globally it is not.
I mean, locally is flat?
Euclidean locally is flat, yes. Okay. Locally is Euclidean, but globally is not. For example, the surface of the Earth. It's a two-dimensional, right, space. Locally it's Euclidean. If I'm just looking here, if I go to around each point locally, I can I can make it as flat as I want by getting as close to the point as I want. But globally, it is not flat. If I go in one direction, I keep on going, eventually I'll get back here. That's never going to happen in Euclidean flat space. Okay? So that's called a manifold. So I can choose a point on the manifold, and I can look at the vectors that go through that point. Okay? But if I have 2 points, my P and Q, the vector going through P and the vector going through Q, I'm not really able to connect them. What do I mean by vector going through P? Let's first be a little bit more precise here. What does it mean? What do I do?
That this point lies.
Yeah, I'm just taking the tangent to that surface. Okay, so think of a flat. Now just take a cartoon. I can think of that as a manifold in a way, right? And then I take something which is, I can look at here, right? Here. Right, this is tangent to a point, it touches a point. Okay? So I can think of all the vectors that go through a point in that space, P, that manifold. And the set of all vectors that go through that point P, what about it? Of course, there are infinite number of them. You can go any direction.
Yeah.
What do they form? Yeah. More generally, this is two-dimensional space. So it could be three-dimensional. N-dimensional space. Of course. How do we call these? Hub. Right. It's called the tangent space. The tangent space to P, and we denote it by TP. TP is the tangent space, vector space, to the point P. So, going back, the vectors belong to a single point. Of course, in Euclidean space, you don't see that. We have an arrow, so we don't know if this arrow could be moving in each direction. No. Vectors actually belong to a given point in space. Put the point P here. Whichever. So, a vector is any quantity whose components undergo this transformation when the coordinate system is transformed in that way. And it belongs to a single point P. And the set of all vectors belong to P forms a vector space, which is called the tangent vector space to P. Go to Sendo. What's your linear algebra?
Let's see.
We'll see. We're getting it. Okay.
Can I ask a question?
Yes.
Why in the definition will we have a V alpha transformation and X alpha transformation?
X alpha is the coordinate.
Okay.
V is a general vector.
Ah.
Doesn't have to be the coordinate. It can be other things. Velocity, momentum, anything.
Yeah, but we're talking about components of vector, and
What components of vector is?
X is just like
X is the coordinate system. This is X.
But they said that this is a vector for vector, right?
This is a vector, yes. This is a vector, and this is how the components of this vector transform under Lorentz transformations. Okay. Now we said so all the set of all vectors the set of all vectors in the set of all vectors through P form a tangent space TP. TP is essentially an abstract vector space. You know that from the first class in linear algebra. It has a set of rules, and of course it fulfills all these rules. So we can think of TP TP is an abstract vector space, and it has all the everything you know from linear algebra, basically, right? Which means that if you have two vectors that go through TP, you can add them, you can multiply them with scalars, right? It's linear way. So for any two vectors V and W that belong to TP, and any scalars, any two scalars A and B, okay. Then have A plus B, B plus W is AB plus AW plus BB plus BW. Same thing you saw already. There is, of course, a zero element. There is a zero element, right? B plus 0 equals V. The other structures, right? There's an inner product, dot product, which we can put in. Right now we don't need that, so just leave that. We'll get it. So slowly. So far everything is clear? I'll ask you what is a vector, I didn't answer. Okay. Okay, now basis. So if we have a vector, a vector space, then there is a basis for a vector space. What is a basis?
It's a set of linear independent vectors.
Mm-hmm.
So that you can represent any vector
basis.
in such space.
Basis.
Yeah.
Basis of the vector space. So, said two things. So, it's basically any set of vectors that what? Has to fulfill two conditions. What's the first condition?
They are linear.
Orthogonal?
Hmm?
Orthogonal?
No, basis doesn't have to be orthogonal.
להיות ליניארית.
Yeah. Linearly independent. What's the first one?
The dimension.
What's the first requirement?
The number of such vectors have the same dimension space.
That is an outcome.
Ah, okay.
What is the first one? If I give you two vectors, can there be a basis for the three-dimensional Euclidean space? Why not?
Because not in the same dimension of space.
So what?
By two vectors, you can represent only other vectors in the same flat.
Yeah.
You can go to.
Yeah. So that means what? In your active, I was a long time ago.
There is a name for that.
Yeah, they span the space. פורסים את המרחק. Span the space. Meaning that right, any vector is a linear combination of the basis vectors. Right? Any vector is a linear combination of the basis vectors. And linearly independent, there's no vector in the basis vectors is a linear combination of other basis vectors. יניב. שכחנו? לא אגיד לכם פשוט סתם. So for a given vector space, how many different bases there are?
One.
One?
Infinite.
Infinity.
Okay, yeah.
For a given vector space, I can think of infinite number of bases.
Yeah.
But what's in common for all these bases?
These two conditions.
Of course. What does it mean? Now count what you said. How many vectors will be in each base?
N.
The dimension of the space,
Yes.
which we call D, right? So there are infinite number of bases, but all of them contain the same number of vectors, which is the dimension of the space. Maybe I should write it down just to make sure that. So, for a given vector space, there are infinite number of bases, legitimate bases, each basis, each one consists of the same number of vectors, which is the dimension of space. So, now, of course, what's the dimension of the Minkowski space? 4. Of course. Do I need the basis to define a vector? No. Maybe I should ask you a different question. Let's say that I'm changing the basis. What happens to a vector? What happens to the vector when I'm changing the basis?
To the vector itself?
Yes, nothing. The vector doesn't care about the basis. The thing that changes are the components of the vector.
Okay.
As we had, right? Put a vector here. Right. Maybe I should do it. And now I'm changing the. Let's do it a little bit more precise. So, this is my space. This is a point P. This is a tangent space. This is my vector. Now I can choose a basis coordinator, which can be, this can be my basis, or I can choose a different basis. Components of the vector on each basis are different, of course, but the vector itself doesn't care. It's important. You know all that, in a way, but there is a very good reason why I'm spending so much time retelling you something which you already know, theoretically at least. Yeah? You're all with me? Good. I write it down. Vector vector is perfectly defined by itself, regardless of its decomposition into components. With respect to any basis. Any arbitrary basis we may choose. That is something which is actually quite crucial in physics in general. You see that there is the physics and there is how we want to describe the physics. So the coordinate is something which we do for us to help us talk to each other. But the physics doesn't know about the coordinates. It will do the same. Right? It's our choice of using, for example, scaling of kilometers, meters. In the US, they use miles, not kilometers, feet. It's a choice. It doesn't matter, it doesn't change the physics. It doesn't change the real distance between two cities, for example. It just changes how we measure. Yeah, that's it. Okay. So look again at this tangent space TP. This is TP. tiniest space of point. And I choose a set of basis vectors. So a set of basis vectors, I'm going to write a set. So I choose a set of basis vectors. I'm going to call these at P, right? For TP at P. And I'm going to call that, it's a very subtle notation, E hat mu with parentheses. And of course mu is CT x, y, z. Actually, that's the way it should be written. Or mu 0, 1, 2, 3. Now we can choose whatever set we want, but for simplicity, we're going to take that aligned with the coordinates x, y, and z. We don't want to mess our life too much. So E1 would be in what direction?
1, 0, 0.
The x direction. The x direction. Now the subtlety of notations, right? When we wrote x mu or v mu, what is the v mu representing?
For vector.
Yeah, it's 4 components, right? v1, v2, v3, v0, these are components of a 4 vector, one vector. But this e mu, know that I use a lower index, and I put the parentheses, it represents what? Represents 4 different vectors. 4 different vectors, each one is a basis vector. Okay, so this is 4 different basis vectors.
It's always going to be 4.
In Minkowski space, yes. You can think of higher dimension theories of physics that will be something else. Right now, we stick to 4. You can do the same thing that I said before. You can do it in 3-dimensional Euclidean sense. Actually, do it. You just don't know that. Forget it. When you're working in non-Cartesian coordinates, just spherical coordinates, or cylindrical coordinates, you're doing exactly the same thing. You just don't know it yet, but you'll see. So that's why I put these parentheses. This is why it's a mu in parentheses, to make sure that we understand that it's not components of one vector. So that means that if we have a vector A, so a vector A can be written as what? A is what? It's A mu, E mu, right? Really, it's a sum. What are A mu?
Coordinate vector.
The components of A, of the vector A. A mu are the components of the vector A in the basis E mu. Okay? And of course, if I change the basis, then the components will change. What happens to A? Nothing. A is here, it's not going to change. Right? And another thing is that, I put the mu as a lower index so that I can make use of Einstein's summation convention. That I have one upper index and one lower index, so I'm really summing over. Okay? classical example of a vector, so example, which is going to be basically again. So example, example of a vector. So again, slowly, gradually we get into it. Let's say I have a space, right? And the space in general is not flat. Right? We said it's a manifold, so locally it is flat. What can I do in an unflat space? Well, there are certain things I'm allowed to do, and there are certain things I'm not allowed to do. Right? One thing, for example, is I can take a hike along that, right? I like to hike, so I can set a path along this space. That's allowed. Right? And then I can specify some parameter along the path. Right? For example, let's say I'm going on a hike. Right? Then I can tell you where I am, and I say, okay, this is my path. And there is a parameter lambda, right? So this is lambda equal to 0, lambda equal 1, lambda equal to 2. Then you can give me a call, ask, hey, where are you, Asaf? Like, oh, I'm in lambda equal 5. Yeah. And you know where I am, right? I specify a path, and I'm allowed. Right? Now, along each point along this path, right, I can form a tangent vector space. Right? That is allowed. And I can specify coordinates. Again, this is allowed because we said that the manifold is locally Euclidean. So there's no problem locally setting up a Cartesian coordinate space. And then I can specify the coordinate as a function of the parameter lambda. So we can specify a vector. So example is a tangent vector to a curve. So I can set coordinates. Whatever. And then I can set the coordinate as a function of the parameter. So for example, x mu of lambda. It is allowed. So the tangent vector right, v of lambda has components of v mu is the x mu over I wrote e, but I should write x. x1 and x2. And the entire vector v is as we wrote before. V mu e. We'll have very thorough discussions about that in what comes.
X1 and X2 is not basis vectors.
No, these are. These would be vectors. That's a good point. No, x mu are the coordinates. I'm sorry. X will be the coordinates. These are not the basis vectors. These are the coordinates like we had before. X mu are the coordinates. X mu, exactly what we had before. Ct, x, y, z. the same coordinates that we had before, and they can change as we go along the curve. Easier to think of it in terms of flat space-time. This is a flat space-time. X and Y. And I put a curve here. Lambda. Right? And the vector would be tangent to the curve. It would look like that. Right? What do I have here? The x over the lambda, dy over the lambda. What are the components?
Basically gradient.
Wait, we'll get to the gradient in a second. Look, this is a vector, it's not a gradient yet. But one thing at a time. Okay. Now I want to look at the transformation law of the basis vectors. Transformation law of basis vectors. So we have here, if you have a vector v whose components in any given basis look like that, so v is witness v sum v mu e. If I'm looking at another basis, e u prime, how's that vector going to look like?
V mu prime.
So v, say u prime, e u prime. So the vector doesn't change. What's the transformation law of the components from v mu to v mu prime? You already know how to make this transformation.
Is Lorentz transformation?
Lorentz transformation, of course.
So it's
So v mu prime I can write down as what? Lambda mu prime mu v mu. V mu prime. Of course, this is true for any component v mu, which means what? Then obviously e mu must be equal to lambda mu prime mu e mu prime. This is the old basis. This is the old coordinate system, right? This is the new coordinate system. This is the old basis, this is a new basis. So I express the old basis in terms of the new basis. I want to express the new basis in terms of the old basis. Right? So I need to invert. What do I do?
Just inverse the matrix
I
and
invert.
Yeah.
What do I use? So what is lambda?
this matrix.
It's a Lorentz transformation.
So we do that.
So we have the opposite Lorentz, and the inverse of the Lorentz transformation. Well, what is an inverse of the Lorentz transformation?
Transpose.
It's also a Lorentz transformation. Just the opposite. Right? From my frame to your frame, it's one transformation. From your frame to my frame, it's the opposite transformation. Right? So I'm going to use a new notation. So lambda minus 1 u prime Any idea how I'm going to write it? Since it's a Lorentz transformation by itself, it is a Lorentz transformation. So I'm going to write it with the first one will be a lower index, and the second will be an upper index.
It's just a notation.
Yeah, of course, it's just a notation. Yeah. And if I use that, then I can write down the new basis E nu prime as a what?
Mu
U prime mu E mu. I'm quite good with my notation, right? Mu is a dummy index, yes, and I have one lower index and one lower index here. So the basis, the set of basis vectors transform as the inverse of the Lorentz transformation. So the inverse transformation of the components of a vector. It's not as hard as it might sound, because I don't like the looks in your faces right now. Okay? So the set of basis vectors transform as the inverse Lorentz transformation of the coordinates. Or of vector components. Well, of course, this one we can also write in slightly simpler form by lambda mu prime mu lambda sigma prime mu is what? It's the inverse Lorentz transformation. And Lorentz transformation, it's a what? It's a chronicle delta, right? Mu prime, sigma prime. Remember, this is the only tensor or vector. It's a tensor, right? That I'm allowing to write with one component on top of the other. The other ones I'm not allowed to write it. And of course, lambda nu prime mu lambda mu prime sigma is delta mu sigma. And I put a note that the textbook by Schutz uses a slightly different notation than that. This is a standard that you'll find in all textbooks. The Schutz uses a different one. And that's actually the origin of the term contravariant. Because the transformation law of the components of a contravariant vector are different and are the opposite, right, to the transformation law of the set of basis vectors. That's why it's a contra. Are all vectors contravariant vectors?
I guess.
Not necessarily, right? So we can think of objects. The transformation law is the same as the transformation law of the basis vectors. Set of basis vectors. Right? These objects You know how we call them? You want to guess how we call them?
Pseudo vectors.
In a way, no, it's not pseudo vectors. These are called covariant vectors. Covariant vectors. And the dual space. What are dual vectors? You've seen that in linear algebra. I know. What is a dual space? Very quiet. What is a dual space, guys? There is a vector space and there is a dual vector space. You know that, right? You must be joking. מרחב הדואלי? אני שואל ברצינות. אתם never saw that in linear algebra?
Probably, but because
Hold on.
I never use it.
Hold on. מרחב דואלי. אלגברה ליניארית. לא?
אני לא זוכר.
לא זוכר. ואת גם לא זוכרת? מה זה? Vector. This is a vector, right? What is that? It's a vector. That's a column vector. That's a row vector. Right? They don't belong to the same space. So they're still connected to each other. How do they connect to each other?
By matrix.
Okay, guys, something there. Who taught you linear algebra?
עמוס.
וזה לא הופיע? So, for every space, TP, there is a dual vector space, which we call TP star. It's also known as the cotangent space. It's okay, I'm defining it right now. If I'm giving you a vector space TP, then there's always a dual vector space. Who lives in this vector space, in this dual vector space?
Also vectors.
Yes, but they're not the same vectors. Right? We spoke about contravariant vectors.
Yes.
The ones that you're supposed to see that live in this space is called linear mappings. What is a linear mapping? So the dual vector space TP star consists of all linear mapping with linear maps. Linear maps from the original space TP to R. Regarding quantum mechanics, what is bras? What are bras?
Fictional vectors.
What are cats?
State vector.
What are cats? You've written that many times, right? What is it? What is that cat? Tell them. In this course you learn everything. What is that? That is a vector in Hilbert space. Right? This represents the state of a system in the Hilbert space, right? And what is a bra? What is that? What is in here?
Scalar.
That's a number.
Yeah.
Right? It's a complex number. That belongs to C.
It's dot product, basically.
This is a number, right? So I can look at phi as a bra, as a mapping from psi to the complex number. Right? So give me a psi. If I'm a phi, give me a psi, I'll give you a number. That's a linear mapping. The same thing, right? If I can think of a covariant, contravariant vector as a vector, right? I can think as an element in the dual space as a row vector that when it acts on a vector, what do I get? A number, right? Which is the inner product, which we call, right? Yeah, you agree with me? So the general structure is very simple, right? Cotangent space consists of all objects. Right? Think of them as objects, right? Abstract objects that are really linear maps of an object within TP to R. Okay, so for example, and this has to be done in a linear way. Meaning what? So let's say that V and W are vectors, so they belong to TP. Okay? And A and B are scalars, just numbers. And let's say that omega is an object that belongs to TP star, to the dual space. What does it mean? That's also called a dual vector. It means that omega that acts on A, V plus B, W. This is a vector, right? Because it's a TP is a vector space, so any linear combination of two vectors is a vector. Is equal to what?
Some number.
Right. It's A times omega that acts on V plus B times omega that acts on W. Right. Listen carefully to how I phrase it, right? It's omega that acts on, and that gives me a real number.
Yeah.
That belongs to R. You look totally unhappy.
The dimension of those space have to be the the same as dimension of original space?
Yes.
So in any case, it's just that product. Yes.
No, I didn't say it's not. I said it is a object that can act on any object within TP and gives me, so I can think of it as a, Pac-Man, whatever. Black box. Right? A linear mapping for me is like a black box. It's not that different than the operator which you see. Right?
But I mean,
What is an operator?
it's also linear, some sort of mapping, not
Nice. Operator. You've seen operators in your right? That you've seen, for sure, right?
Yeah.
How do we represent an operator? Matrix. Why? And then you get what happens when an operator acts on a vector.
Gives another vector.
Another vector, right? So, operator, I can think of it as a black box. Okay, purple box, right? Gets a vector in, gives me another vector out. Don't have to live at the same world, right? This can be an n-dimensional, this can be an m-dimensional, right? Same way, it's linear mapping. That's why I'm surprised. If you've seen operators, then why didn't you see dual space? Right, linear mapping gets an vector in, and out I get a number, which belongs to R. Same thing. Simpler, actually. So, inside here, there is a monster that takes a vector and gives me back, in return, a number. And it does so in a linear way. I get two vectors, I add them, I get something which is the addition of them. Yeah? I don't know why you're not happy. So. Okay. So, now obviously, if I look at all the objects within the dual space, right, by themselves, they form a vector space. Right? So all objects within TP star form a vector space. Right? Namely, if omega and eta belongs to TP star, that means that A omega plus B eta that operates on V is equal to what? A omega operates on V plus B eta that operates on V. If you get confused again, think of this row vector versus column vector. They don't belong to the same space. You cannot add them. But you can take a column vector and operate it on a row vector. And you get a number. Okay? What's the next thing that we're going to have? So if these objects form a vector space, then what does it mean? They has a basis, right? I can form a basis for that vector space now for TP star, right? So I can look at the basis for TP star. So you can set a basis of dual vectors. So these are also called dual vectors. Right? Dual vector space. So we have dual vectors. So we can now look at the introduce a basis of the dual vectors. Which you're going to denote by theta with an upper index, obviously. Let's say here. And what's going to happen when a basis vector from the dual space operates on a basis vector from the real space, the real vector space? What am I going to get? This is an object, a basis vector, of course, delta, right? Conical delta. Right? So this is going to be a delta mu nu. So similar to regular vectors, any object in this dual space we can write as omega is equal to omega mu theta nu. And how do we call any object of TP star? Well, we basically said it's called a what?
Covariant vector.
It's a covariant vector. It's called a dual vector. Another name indeed is a covariant vector. A third name is called one form. Because there is an entire theory of called P forms, which is really cool, but I don't know if we'll get into that. On the one hand, we could get it because there is a small class, so we could go. But then it depends on how much you follow. There's no point of going into things that are not necessary for you to understand GR. It's just confusing. So I'll see how well you do. Using this component notation, so omega of V, right? Omega mu V nu theta mu that acts on E mu is omega mu V nu delta mu nu is omega mu V mu, which belongs to R. So for that reason why we don't really use these basis vectors. We don't really need them. You can simply do the components, and they're good for us. Okay. Now, because of that, we can also think of V as the dual to the dual. Right? So the dual space to the dual space is the space itself. Right? It's going to make sense, right? So I can write down. Really define V of omega is omega of V, which belongs to R. So the dual space to the dual space is the space itself. I think it's a good place to stop here. Any questions? Okay, I'm a little bit surprised you didn't see that. Actually, I'm more than a little bit. I am surprised you didn't see that. But okay, it's good that you see it here. So normally it should be part of your linear algebra course.
Why we can say that this is just dot product?
It's not exactly a dot product, it's an object that operates on another object. But you'll see that the dot product, we'll define it properly next time, but you'll see that the dot product is, we'll define it. We'll see.
Is there a difference between dot product and inner product?
No, it's the same.
Okay.
We'll see.
I also have a question about pseudo-vector, for example, angular momentum. It's not a vector.
We're not going to touch it right now. It's not exactly part of what we do right now. Let's do one step at a time. Okay? There is a good reason why I want you to do one step at a time. Although pseudo vectors are not so much in this course, it's more in QFT. We touched that, but forget it. All right. Maybe just one thing before we go. The transformation law of the component of the dual vector, the same as transformation law of the basis vectors, right? So we have omega transformation law of components of dual vector, omega mu prime is obviously lambda mu prime mu omega e. And for the basis, of course, mu prime is lambda mu prime sigma theta sigma. And on the side, like if we have a V, V1, V2, Vn, and omega, I will write as omega 1, omega 2, omega n. Omega operates on V. Here's what?
Omega 1, V1.
All right. Any more questions, guys? Okay. You're still with me? Yeah. New things. I'm surprised it's new, but that's why we're here.
Can you get in the lambda the lecture summary?
What?
Can you get on the lambda the lecture summary?
All right. See you on Thursday, guys.
Thank you.
לא למדנו את זה בליניאר, נכון?
עשיתי לינארית במתמטיקה, אבל לא למדנו את זה.
זהו. לא שמעת, כאילו אני זוכר שאולי שמעתי את המושג,